MEMS is a new engine management system for fuel-injected cars. It replaces the hot wire system on Montegos from June '89. MEMS stands for Modular Engine Management System. It controls both fuel and ignition and will form the basic fueling strategy well into the 1990s. The MEMS Montego is capable of running on unleaded as well as 4-star leaded fuel. This video is designed to explain how the system works, how to service it, and how to diagnose faults in the system. The MEMS system was developed alongside ERIC, currently fitted to all carburetor Montegos. MEMS and ERIC share many features. They have similar programmed ignition and idle speed control systems. Both ERIC and MEMS keep a record of intermittent faults, which can be read and checked out using microcheck or COBEST. So what else is new about MEMS? The most striking difference as you look under bonnet on a MEMS Montego is the air cleaner box. This contains a silencer to reduce intake roar. MEMS calculates the air-fuel ratio by the speed density method, so the flow meter used on hot wire has been deleted. The throttle body is completely new. The idle air valve used on hot wire has been replaced with a stepper motor which opens and closes the throttle disc to control idle speed. But that's not all. Ignition timing is used along with the stepper motor to improve idle quality. The throttle potentiometer is now fixed and requires no adjustment in service. There are 2 breather pipes on the throttle body, one each side of the throttle disc. These provide depression for the crankcase breather system. The pipe on the engine side of the throttle disc has a restrictor to prevent oil being drawn into the engine in overrun conditions. The oil vapor separator has been moved to the back of the engine. Moving on to the fuel system. The fuel feed rail is now forged alloy. The injectors are connected to the fuel rail. Fuel flows from the pump through a filter before reaching the rail. Fuel pressure in the rail is kept at a constant level above inlet manifold pressure by a regulator. This operates in the same way as that on the hot wire system. A solenoid is fitted in the fuel return line of automatics to improve hot starting. The main relay, fuel pump relay and starter relay are contained in the multifunction unit, or MFU. ERIC and 1989 model year hot wire Montegos use the same MFU. The manifold pressure sensing hose now has a fuel trap to protect the pressure transducer inside the ECU. Inside the car, there are a couple of important changes. Firstly, the inertia switch is now behind the dummy glove box, next to the in-car fuses. And secondly, a throttle switch is fitted to the throttle pedal. This informs the MEMS ECU when the pedal is pressed or released. So that covers the hardware changes to the new injected Montegos. But how does MEMS actually work? There are 4 injectors, one for each cylinder. These injectors have built-in solenoids and are controlled by the MEMS ECU. All injectors open at the same time and inject a fine spray of fuel into the back of the inlet valves. This atomized fuel is then held in the manifold until the inlet valves open. To cater for different operating conditions, the ECU varies the amount of fuel injected. It does this by opening the injectors for a longer or shorter period, or adjusting the injector pulse width, as is known. Adjusting the amount of fuel delivered is relatively easy. The difficult part is deciding how much fuel to inject in the first place. The ECU determines air-fuel ratio using a speed density calculation. So, what is speed density? Let's take the example of an engine at idle. The throttle disc is virtually closed, causing a vacuum or low absolute pressure in the manifold. Now, air at a low pressure is thinner, it has a low density. When this thin air is drawn into the engine, a relatively small amount of fuel is needed to obtain the correct air-fuel ratio. If we look at the other end of the scale, with the engine at full load, there's now a high pressure in the manifold. When the inlet valves open, a full charge of dense air is drawn into the cylinders and the ECU injects more fuel to achieve the correct ratio. The MEMS ECU measures the pressure of air in the manifold through a vacuum hose and calculates the speed of the engine with a crankshaft sensor. Although the pressure of intake air gives a good indication of its density, temperature also has an effect. For instance, air at atmospheric pressure will have a lower density when it's hot than when it's cold. So to fine-tune the calculation, the ECU measures intake air temperature through a sensor at the rear of the air filter box. So the speed density calculation enables the ECU to determine basic fuel delivery. That is, the injector pulse width needed to suit a variety of engine speeds and loads. But to meet all operating conditions, this basic fueling calculation must be constantly updated by secondary sensors placed around the engine. Now the ECU needs to know the temperature of the engine. A coolant sensor in the thermostat housing provides this information. When the engine is started from cold, the ECU enriches the mixture. As the engine warms, the mixture is gradually returned to normal. The result is excellent cold drivability and fuel economy. Next, the throttle potentiometer. This provides an early warning of throttle movement. During acceleration, the ECU receives a rising voltage signal from the potentiometer and increases injector pulse width to prevent flat spots. Put simply, the throttle potentiometer is serving a similar function to the accelerator pump on a fixed-jet carburetor. The throttle switch is also an important part of the MEMS system. When the driver has his foot off the pedal, the switch contacts are closed. This signals the ECU to implement idle air-fuel ratio and to control idle speed. But it will only do this if engine speed is below a certain level. When the throttle pedal is pressed, the throttle switch contacts open, and the ECU switches over to its main fueling program. Incidentally, if the throttle pedal is off and engine speed is high, the ECU deduces the engine is on overrun and will implement overrun fuel cutoff to improve fuel economy and exhaust emissions. Vehicles with manual transmission have a temperature sensor in the fuel rail. When outside temperatures are high and the engine is switched off, under-bonnet temperatures can soar. This sensor informs the ECU when fuel temperature is high. The ECU then increases injector pulse width as the engine is cranked to quickly clear any vaporized fuel through the injectors, which could otherwise cause difficult starting. When you've restarted a hot engine, you may notice a slightly higher idle speed. This is completely normal. Engine speed will return to normal after a short period. Automatics have a different system, which isn't controlled by the ECU. A temperature switch is fitted in the fuel rail. This operates a solenoid in the fuel return line. When the fuel rail temperature is high, the switch energizes the solenoid to form a restriction in the return line. This increases the pressure of fuel in the rail to raise its boiling point and quickly convert any vapor back to liquid. For a complete breakdown of these sensors and their function, refer to the booklet that accompanies this program. Now, idle speed control. MEMS has a stepper motor, which opens and closes the throttle disc to control idle speed. Now, an interesting feature of MEMS is the way in which ignition advance and retard are used to help the stepper motor maintain a stable idle. When the engine is cold, the coolant temperature sensor signals the ECU to index the stepper motor and give a fast idle speed. This fast idle gradually decreases until normal operating temperature is reached. At normal temperature, the ECU controls idle speed to 750 plus or minus 25 RPM. Incidentally, this idle speed cannot be adjusted. When a load is placed on the engine, for example the alternator loading from the heated rear screen, a control sequence is triggered. First, the ignition is advanced to bring the idle speed up to its programmed value. While this is happening, the stepper motor indexes to take over the role of controlling idle, and the ignition then retards to its nominal value. So, MEMS idle speed control is a stepper motor and ignition timing, working together to provide a stable idle. Another important element on the fuel injection side of MEMS is the fuel pump control system. The fuel pump is controlled by the MEMS ECU. When the ignition is first turned on, the ECU energizes the fuel pump relay in the multifunction unit for 1 second to pressurize the fuel system. The fuel pump is fed current through a ballast resistor to reduce pump output. Under cranking, the ballast resistor is bypassed and the fuel pump is fed full battery voltage from the starter circuit. This counteracts the current drain placed on the system by the starter and ensures that fuel system pressure is always maintained. When the engine's running, the ECU operates the fuel pump continuously, supplying current through the ballast resistor. Now, ignition control. Although ignition and fueling are now controlled from the same ECU, the MEMS ignition system is essentially the same as the existing programmed ignition. Inside the MEMS ECU is an amplifier. This performs a similar function to the contact breaker points of a conventional system. It switches the coil on and off. In a conventional distributor, you have a cam to open the points when the engine reaches a certain position, a centrifugal advance mechanism to advance the timing as the engine turns faster, and a vacuum advance system to advance the timing under light load conditions. The MEMS ignition system meets all these basic requirements, and more. The crankshaft sensor tells the ECU the exact position of the engine and its rotational speed. The manifold pressure signal provides information on engine load. Just like the conventional system, these speed and pressure signals are used to calculate basic ignition timing. This basic setting is then fine-tuned, depending on signals from the NOx sensor and coolant temperature sensor. Finally, a signal from the throttle switch is used to tell the ECU when the engine is at idle. It then uses ignition advance and retard to help the stepper motor maintain a stable idle speed. So, the ECU is in complete control of ignition, fueling and idle speed. It calculates the exact air-fuel ratio using the speed density method and ignites this mixture with split-second accuracy. The result? Performance with economy. Now, the basic servicing requirements of the MEMS system on Montego. The air filter should be replaced every 24,000 miles and the fuel filter every 48,000 miles. Apart from the filters, servicing is limited to checking the exhaust CO content and setting the throttle position speed. This is performed at the 1,000 mile after-sales service and every main service from then on. CO and throttle position speed can only be adjusted using microcheck or co-best. Microcheck leads you through a sequence to either tune the engine or diagnose faults in the system, adopting a similar question and answer philosophy to co-best. A printer supplied with microcheck can be used to give hard copy, a printout that's proof of your test and tune results. Whether you use microcheck or co-best, it's important to follow the operating instructions. We'll use microcheck as an example, because it's relatively new, but co-best will lead you through the tuning sequence in the same logical step-by-step manner. So, How do you tune a MEMS Montego? As with any vehicle, the first thing to do is to carry out the preliminary checks on the engine and the fuel system. Make sure there's a clearance at the throttle cable lost motion link. On automatics, the kickdown cable must have some free play. When the car's ready for tuning, make sure the CO meter is ready for use. Then warm the engine and transmission to the equivalent of a 2 to 4 mile road test. It's most important to warm an automatic vehicle on the road. A static warm-up won't heat the transmission oil fully, leading to false CO readings. On return from the road test, connect the microcheck to the battery and then to the serial diagnostic link. Insert the MEMS program card, ensuring it's the right way up, and press the F2 button. You're now asked whether you wish to enter a test or tune sequence. Press Diamond for tune. Microcheck now guides you through a tuning procedure. Follow the on-screen instructions and answer any questions, pressing star for yes and hash for no. During the sequence, you'll be asked to check the CO content. If it's out of adjustment, press Print to increase CO and Diamond to decrease it. One button press gives about 0.25% change in CO. When the CO content is correct, press star to proceed. Microcheck now monitors the position of the stepper motor at idle speed. If it decides the stepper motor is either too far open or closed, it will index the stepper to a known position and ask you to set the throttle position speed. Microcheck tells you whether the speed needs to be increased or decreased. Loosen the lock nut and adjust the throttle position screw under the stepper motor until the correct speed is achieved. You'll need a 7mm spanner for this. If during the tuning sequence the throttle position screw was adjusted, Microcheck will remind you that the throttle and kickdown cables will need resetting. With the engine idling at normal operating temperature, check the kickdown cable adjustment. There should be a gap of 0.5 to 1 mm between the crimp and the cable outer. Adjust the cable outer length if necessary. To adjust the throttle cable, first pull the cable outer from its bracket. Pull on the cable to remove all free play from the cable and lost motion link. With the cable held in this position, screw the square nut up to the back of the bracket. Now, with the nut held in position, refit the cable into its bracket. When tuning is complete, you can connect the printer and obtain a printout of tune results. So that's just about all you need to know about the day-to-day servicing of a MEMS Montego. Now let's take a look at how Microcheck and Cobest can be used to diagnose faults. Again, we'll use Microcheck as an example. Connect in the same way as before, but this time the engine doesn't need to be warm. Select Test by pressing star. Microcheck will then guide you through a test sequence, checking the integrity of the ECU and all its various inputs and outputs. If Microcheck highlights a fault, you'll be taken through a corrective service procedure. Instructions are displayed to help you pinpoint the fault quickly. On some of these tests, you may be asked to probe the ECU connector with a digital multimeter. You'll find this easier with the plastic cover removed, but always refer to the Microcheck guide. The guide contains schematic diagrams for each individual circuit in the MEMS system and details the correct procedure to follow when checking for continuity, voltage and resistance. A feature of the MEMS system is its ability to record certain intermittent faults. A loose coolant sensor connection, for instance, can make and break several times before giving out altogether. As you know, faults like this can be difficult to find. On a MEMS car, there's no problem. When the fault first occurs, the ECU remembers it. This memory will be held, even if the fault should correct itself. When you next carry out a system test with microcheck or co-best, a list of these intermittent faults are displayed. One important point to mention is that when a microcheck or co-best tune procedure is performed, any record of intermittent faults are erased from the ECU memory. So, if you suspect there may have been a fault at some time, make sure you carry out a test sequence prior to tuning the engine. Something else to bear in mind is that when part of the system is disconnected with the ignition switched on, the ECU will remember this as an intermittent fault. So, if you want to avoid chasing intermittent faults that don't exist, make sure the ignition has been switched off for at least 30 seconds before disconnecting any part of the system. As we've already seen, the MEMS system stores the idle and fueling characteristics in its memory. Consequently, whenever a new ECU is fitted, or one is swapped from another vehicle, you must tune the car with microcheck or co-best. There's one very important item that can't be tested with microcheck. That's fuel pressure. The MEMS system needs a constant supply of clean fuel at the right pressure. If the fuel pressure is too high, a rich mixture will result, and if it's too low, the mixture will be weak. To check the fuel pressure, you'll first need to depressurize the fuel system. Pull the button on the inertia switch up to isolate the fuel pump and crank the engine for at least 20 seconds. The engine may run for a short time until fuel pressure drops off. Now reset the inertia switch. Incidentally, if you're using co-best, the fuel system is depressurized automatically. Connect the fuel pressure gauge, or the co-best pressure transducer, to the supply side of the fuel rail using the correct adapter. Then disconnect the vacuum hose from the fuel pressure regulator. Start the engine and check fuel pressure. Look for between 2.4 and 2.6 bar at idle. Now reconnect the vacuum hose. Fuel pressure should drop to around 1.8 bar. If it doesn't, examine the hose for splits and blow down it from the regulator end to check for blockage. Turn the ignition off and make sure the system holds pressure. It shouldn't drop more than 0.7 bar in the first minute. If it does, clamp the return hose from the regulator to the tank. If the pressure now holds, the regulator is faulty. If the pressure still drops, the leak must be in one of the injectors or the fuel pump non-return valve. To check the non-return valve, clamp the fuel feed line. If the system now holds pressure, the non-return valve is faulty and the pump must be replaced. To check there's a reserve of pressure from the pump, start the engine and clamp the return hose for a maximum of 1 second. Fuel pressure should rise by around 2 bar. If it doesn't, check for a blocked fuel filter or restrictions in the supply line before replacing the pump. It's important when performing this test not to exceed the gauge maximum reading. A word of warning. Fuel hoses must not be clamped for longer than 10 seconds, and only the approved Girling brake hose clamp can be used. Prolonged or excessive distortion of these hoses can cause damage to their lining material. That's a brief look at the operating principles, servicing requirements, and routine fault diagnosis procedures of a MEMS Montego. To round up, let's recap on the main points of the program. MEMS controls ignition, fueling and idle speed. MEMS uses the speed density method to calculate air-fuel ratio. Ignition timing and a stepper motor are used to control idle speed. The throttle switch informs the ECU when the throttle pedal is pressed or released. The inertia switch is now positioned next to the in-car fuses. Automatic cars have a solenoid in the fuel return line to aid hot starting. The kickdown cable on automatics must be adjusted and checked with the engine running. MEMS can remember certain intermittent faults. These can be read with microcheck or cobest. The throttle position speed and idle CO content are checked at the after-sales service and every main service from then on. Use microcheck or cobest to tune and diagnose faults on MEMS. The booklet that accompanies this video contains a detailed breakdown of everything covered in the program. MEMS is the first of a new generation of injection systems. Performance and economy have been designed in to give Rover another major advance in engine management systems.